Okay, last lesson we look at the energy of a mass oscillating horizontally and when it's attached to a spring in a horizontal position, and we have this uh, variation of energy for the Ke and the potential energy of the spring, how it changes from the equilibrium position. Okay, as you can see, it's quite symmetrical about the equilibrium position, where the Ke is maximum in the middle and potential energy is zero at the equilibrium position. Okay, now let's look at a case of the same kind of the same spring and mass. Supposing we put it in a vertical position and allow it to oscillate vertically. Now you find that the energy now there's a new energy being introduced in the system because of the fact that from when the mass move from A to B to C, the gravitational potential energy changes. Okay, so unlike the horizontal case where there's no change in potential energy, gravitational potential energy, we don't have to take into account, but for the vertical oscillation, we have to take into account the change in gravitational potential energy. Also, for the case of vertical oscillation, imagine this mass is being attached from beginning, and when the spring is now loaded at point A, when the spring is not stretched yet, and then you attach the mass at point A, and then you let go and let it fall vertically. From A to B to C, the potential energy increases all the way. Okay, whereas for a case of horizontal oscillation, the potential energy decrease to the middle and then increase back to B. Whereas in the case of a vertical oscillation, from the highest point to the lowest point, the elastic potential energy increases all the way. Okay, so let's look at each of this energy one by one. Okay, let's look at the Ke. Now, whether it's Ke, whether it's in horizontal or vertical direction, the kinetic energy variation is the same because the velocity variation is the same. At the highest point, the velocity is zero, therefore the Ke is zero. At the lowest point, the velocity is also zero, so the Ke must also be zero, right? So those two A and C are the turning points, at the point where they stop and turn back, right? So both at A and C, the Ke's are zero, and is also maximum at the center. So as far as we know, the kinetic energy stays the same as the shape of the kinetic energy variation stays the same as a case of horizontal oscillation. So the shape of the graph is maximum at the equilibrium position and zero at the two ends. Okay, so it's an inverted U shape or the N shape curve, same as before. Right, let's move on to elastic potential energy now. Now, we have at first the mass attached at the point where the spring is unstretched. So the point A, the elastic potential energy is zero. And then the moment you let go, the mass start to fall from A to B to C. So all the way the spring is being stretched. And then when it come back, the extension is smaller and smaller. It just start to decrease back to zero at point A. So as you can see, the extension increases all the way from A to B to C. You will expect the elastic potential energy stored in the spring to increase as well. So the equation is half kx squared. If you remember from the previous chapter, the elastic potential energy is proportional to extension squared. So you will expect when you plot a graph of elastic potential energy, it starts from zero, it increases according to half kx squared all the way until its maximum at point C. Okay, so this is what you expect. So it increases all the way down, right? So if we now plot the EPE graph overlap with the Ke graph is what we have got earlier. So now if we include the elastic potential energy curve, bearing in mind by at point A is zero and it increases by a curve, and this is what you get here, right? Half kx squared, right? So at A equals zero and it increases to point B and to point C. Okay, so it increases in the downward direction. So A is the highest point, B is the lowest point. So it increases all the way down according to this curve here. Half kx squared, right? Or half Ke squared. Okay. Now let's look at the gravitational potential energy now. How the mass as you move from A to B to C, how the gravitational potential energy changes. Now, gravitational potential energy is simply like mgh, where h is a change in height. So as it move from A to B to C and back to B to A, the gravitational potential energy decreases all the way down, right? From A is actually the highest, then it decreases to B and decreases to C. Now, the gravitational potential energy is therefore changed in the reverse direction compared to elastic potential energy. The main difference is that the change in gravitational potential energy is proportional to distance moved. It's not like elastic potential energy. Elastic potential energy is half kx squared. There's a dependence on the displacement squared, whereas um, the change in gravitational potential energy is proportional to displacement. Okay. Now we have the freedom to choose where is the 0 point of gravitational potential energy. For symmetry purposes, we can just say, okay, let's say we keep the gravitational potential energy to be 0 at point B. That means for point A, it will be positive, and for point C, it will be negative, okay? Negative potential energy. So if you want to plot the graph, uh, this is how it look like, okay? Gravitational potential energy, and it is symmetrical about the center, the equilibrium position. The highest point A has a maximum gravitational potential energy. So if you let the gravitational potential energy be zero at the equilibrium point, point C will have a negative gravitational potential energy. Okay, so this is how the gravitational potential energy change with um, displacement from point B. Okay, right. If we add the two potential energy together, the gravitational potential energy and elastic potential energy, we add them together, they will give you the total potential energy, right? If you add the two together, this is called the total potential energy, and the total potential. So you add up the curve, the dotted curve, EP curve, plus the straight line of the GP, uh, the straight line graph of GP, you actually end up with another curve, which is shown here. Okay, the elastic potential energy is actually curved like the one shown in red line. It's actually curving up. It's curving up here from the equilibrium position. So the general shape is actually the same as the case for horizontal oscillation. It is lowest at the middle at the equilibrium position and highest at the two end, except that now the relative position is higher now. Okay, in horizontal position, the rate curve is actually all the way now to zero at point B at the equilibrium position. That now it has been shifted up. Okay, so the total potential energy, which is defined as the sum of elastic potential energy and the gravitational potential energy, actually has the same shape as before, similar to the horizontal oscillation, except now that it is moved a little bit higher than before. Okay, right. So if you add up the total, the 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 elastic, the potential energy plus kinetic energy, add the two together, the red curve and the blue color curve, which represents kinetic energy, you add the two together, you actually end up as before constant total energy, which is shown by the horizontal curve above. Okay, so the sum of Ke plus total uh, potential energy add together, which is actually a total energy, is a horizontal. Um, is a constant value which doesn't change with the displacement from A to B to C. The total energy stays the same. Okay, so the sum of the red curve and the blue curve is actually a constant. The sum of the red curve is actually the elastic potential, the dotted curve, plus the straight line curve, the straight line due to GP. Okay, right. So you must also keep in mind that we have arbitrarily set the gravitational potential energy to be zero at point B, but you could have set it to be zero at point C. So if it's zero at point C, means the whole thing is shifted up. The whole thing is shifted up. The whole gravitational potential energy graph is shifted up. Then uh, every the every term will be shifted up. The elastic potential energy, which is the sum of GP plus EP, will be shifted up, and the total energy will be shifted up as well. So, this exact position of the potential energy curve and the total energy curve depends very much on where we set the 0 point of the gravitational potential energy. Okay, so don't have to memorize exact value of the curve, but all you need to know is that the gravitational potential energy is a straight line graph. At the lowest point is minimum, at the highest point is maximum. You just draw a straight line graph. On the other hand, the elastic potential energy is minimum at the highest point, and it reaches the maximum at the lowest point of the mass. Okay, so this is how you, if you want to memorize this, how you memorize it. Okay, so if you look at the next example here, this question here is about the different curve uh, of the oscillation. In this case, you can see that the gravitational potential energy doesn't start from zero. Uh, okay, it doesn't start from zero. It starts at this is point C. Yeah? The point C is here. This is the lowest point. Okay, this is your point A. This is the highest point. Okay, so all you need to know to recognize the correct answer, pick the correct answer is that the KE is the same shape as before. It's maximum at the equilibrium position. It's zero at the two ends. So the KE is the same as before. The gravitational potential energy is a straight line. It is lowest at the lowest point and highest at the highest point. Okay, so this is the GP is a straight line. And then the EPE is a curve. Now its minimum is lowest at the highest point, and it curves up until it is maximum at the lowest point. So this EPE curve is lowest here and is highest at the and it is a curve. It's highest at the lowest point. And the total energy, the sum of all three, the sum of these three, which is total energy GPE plus EPE plus KE, all the three add together give you a total energy which is a straight line throughout. Okay, so the correct answer for this question here is D. The rest of the curve are not quite correct. If you try to look at them, most of them are not correct. Like for example, A, the EPE is 0 at the center and it move out on two sides. This is obviously wrong. And the GP is also a curve. The GP cannot be a curve. The GP is a straight line. Okay, so the only correct interpretation is answer D. Therefore, okay, right. Let's move on to look at two special cases of that we've been talking about. Look at the equations, right? So this we have been talking about this mass and spring oscillation. Now, the period of oscillation is actually given by this 2 pi square root of m over k. You actually don't have to derive this equation. You may be able to recall this equation used it. If you need to do any calculations, probably you'll be given or you need to recall this equation. The time is proportional to square root of m over k. So the exact formula is 2 pi square root of m over k. So when the mass is big, then your t will be big as well. Okay, so as I said, you don't have to derive this formula. You just need to recognize and then use it and be able to recall it if possible. Okay. Now, so the next example, we have a mass that is attached to a spring that moves with an extension of 0.1 meter, then is pulled down by a distance of another distance of 0.02. Now, in this case here, is because it's pulled down by 0.02, so that is your amplitude. So the first value of 0.1 is not an amplitude. So the original, the spring is like that. You hang a mass there, so it's extended from here by 0.1 meter. Then you pull it down by 0.02. Okay, you pull it further down by 0.02. This is the amplitude. Okay, this is the amplitude, not this one. This is not the amplitude. Okay, this 0.1, this is not the amplitude. So the answer for part A is the amplitude of oscillation is 0.02. The amplitude is amplitude is measured from here, okay, from the equilibrium position, okay, from the equilibrium position, because the 0.1 meter is it's actually below the unstretched length is the equilibrium position, okay. Then to find the period of oscillation, you just um, need to take um, substitute into the equation that we know earlier, um, 2 pi 2 pi times square root m over k, but you're not given the value of k. You're given indirectly by the fact that at equilibrium position, the total restoring force upward kx by the spring equals to the weight downwards. So the upward force equals downward force. This is the equilibrium position. So once you have that, um, you can calculate the value of k. Once you have the value of k, you put inside, you can calculate the value of the period of oscillation. Okay, so the k is given indirectly in this case. Right. Another common example of oscillation is the simple pendulum. Right. This time, the formula is given by this 2 pi square root of L over G. It's very similar to the spring mass case, right? In this case, remember that oscillation must be small angle. Small angle. So angle, when I say small, is less than 10 degrees. So if the angle is not small, the formula is not valid anymore. Okay. So remember when you do oscillation experiment in the lab, try to keep this in mind as well. All the formula that you use for the calculation and all that is always making reference to a small amplitude or small angle. Okay, right. Uh, so in this case here, the pendulum period depends on the length and depending on the free fall acceleration. So in the next example, you have this pendulum that has a period of 1 second at a place where the acceleration free fall is g. Now, if we bring it to another place, let's say the moon or something like that, um, what would be the new period if the new acceleration is g prime? Okay, so you just substitute according to the formula. So in this case, the 2 pi and 2 pi cancels away, and you're therefore left with this straightforward formula or answer as depending on the inverse square root of g. Okay, so as before, you're not required to derive this formula. Uh, you may recall and use this as and when required. Okay, right. We move on to the last section of this topic here, which is on damped oscillation. The word damped here means, or damping here means that there's some kind of external frictional force that takes away energy of the oscillation. Okay, so for example, when object is oscillating in the air, it collides with the air molecules. The air molecules will actually take away the energy and cause the amplitude of oscillation to decrease with time, and over time the amplitude becomes smaller and smaller and smaller. Okay, so we're looking at three examples or three categories of damping. The first one is called light damping, when there's some resistance taking away the energy, so because of that the amplitude will decrease with time. Now the amplitude decrease with this thing called the exponential decrease. This is called exponential decay. Okay, exponential decay with time. Decay means it decreases with time, right? So the general shape is that it will decrease with time. Now, if you increase the resistance force to a larger value, it will take away energy at a faster rate. Then we say we have a higher damping. Then in this case, then the amplitude will fall even faster. Now, when that happens, actually you expect the period of oscillation to increase slightly also. You know, the time taken for it to complete one cycle, when there's a stronger resistive force, you expect it to be a bit larger, but it's not that much. So as far as we're concerned, for A-level exam, it doesn't really matter. That you can draw the new graph with either the same time or a little bit longer time. Both are acceptable. Okay, right. Next, the example 16 here, you're given the four possible answers for displacement of object that is undergoing lightly damped oscillation. So you look at all four of them. Only one of them is correct, which is D. This is the correct one. It shows that the amplitude decreases. Okay, the amplitude decreases exponentially. This is part B is not correct. Part B although decreases, but it's not symmetrical. As in the amplitude one side is larger compared to the other side, so this is not possible. Then amplitude cannot be in, you know, cannot increase back again. Like from here to there, the amplitude seems to increase again, right? So this is not correct. C is also not correct. It shows a very significant increase in the period of oscillation. Okay, this is a very large increase here, right? This is also not correct here. This part here shows a very large increase. A is not correct, obviously, because the amplitude stays the same, right? Amplitude stays the same, then suddenly start to decrease. So this is not correct, right? Right. What happens if we increase to the other extreme? If the damping is so high, we increase the resistance so much so that the oscillation doesn't take place. You increase the resistance force so much that there's no oscillation. Now, this is called heavy damping. In that case, there is no oscillation. When you pull this object one side, supposing you put a mesh inside, you put this oscillator, you put inside some kind of let's say it's very sticky liquid like honey, you 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 push it down and then you let go, you it's almost never going to oscillate. In fact, it will take a long time for it to come back to the uh, original position. So this is called heavy damping, right? This is called heavy damping, right? There's no oscillation. Okay, heavy damping can be used in some applications like in the door closer. In this case here, for example, the door closer with heavy damping allows the door to close in a very slow manner so that it takes a long time. Okay, look at this picture here. It takes a very long time to close and close in a very small force. Okay, so this is how it's being used in an application here. It's a door closer for safety purposes. Right. The next is in between. Then there's a situation called critical damping. This is a situation where the oscillator doesn't cross over to the other side of the equilibrium. There is no oscillation, but damping is just enough so that the system come back to the equilibrium position in the shortest possible time. So the time taken to come back is actually the shortest possible, but there is no oscillation. This is called critical damping. Now, this is also important in some application. Why is that so? For example, in a car, they allow the car when they run over road hump to oscillate a little bit. When you run over road hump, you actually allow it to sort of vibrate a little bit, but you don't want it to continue to oscillate after it crosses the road hump. So you want the passenger in the car to feel safe and comfortable, so that when you run over road hump, it will be disturbed from this equilibrium position. The car will be disturbed from this normal vertical position, but it quickly come back to the original position, so it doesn't oscillate vertically. So this is one example. So it's a car suspension system. The other possibility is the other application is that in a moving coil meter. These are the called old analog meter that uses some kind of coil and electromagnet inside. So when you connect this meter to a circuit here, when it's taking a reading, the meter will actually come to its final position and stop there almost like instantly, so that it doesn't oscillate. Okay, so this is important. So you must design the moving coil meter in such a way that it is critically damped. If not, it will continue to oscillate. So you find that very difficult to take the final reading. It will keep on swinging, and so on. Okay, so this is what happens in a moving coil meter. It must be critically damped so that it doesn't oscillate at the final reading. Okay, in summary, these are the three cases of damping that we look at. The light damping, the one in blue, right? The critical damping is the one in green that comes to the equilibrium in the shortest time, and then the over heavy damping takes a long time to come to a stop. Okay.